Hello, my name is Lieven Penning. I'm the founder and CEO of PlanOpSim, and today I'll be giving you an introduction into the PlanOpSim software for designing and modeling meta surfaces. In this short demo, which will take about half an hour, I'll go through the basic steps in designing a meta lens, starting from the nanostructure design to organizing them to form a small meta lens simulation. So what you see here is the basic overview of the PlanOpSim software. There are two main components to this. One is the metacell module, which we'll use to design the metaatoms, and the nanostructures themselves, which are used to manipulate the response of the incident light. And then in the metacomponent module, we'll use libraries of these nanostructures to design them into functional optical components. When we look in metacell calculations, our goal is always to structure nanostructures in such a way, to design them in such a way that their optical response gives us control over the amplitude, phase, dispersion, any optical properties that we want for our total lens design. We'll start always by defining these 5 basic tabs. On the one hand, we'll first set the geometry of the system, meaning the material properties and the structure itself. Then we'll set the targets, the incident light, and any quantities that we want to optimize for, as well as any simulation parameters under simulation settings. And then finally, we'll run the simulations. Because these nanostructures are sub-wavelength in size, it is important that we simulate them using a full solution of Maxwell's equations. In our case, we use the RCWA solver because it's proven to give accurate solutions to Maxwell equations, and at the same time be very performant in terms of time and memory efficiency for these type of structures. But let's start at the basics by defining our structure. RCWA is built up as a periodic simulation with different geometric layered constraints. So we'll set these here. In a typical meta surface, we'll always start from an incident layer, in this case fused silica, and an exit layer of air, and in between we'll structure our different sizes. So in this case I'm using a niobium pentoxide structure with a thickness that I've given here, and I can modify these of course here. So I've set this to be a circle, but I could easily change this, for example, to rectangular shapes or anything else of my choosing. But let's, for the sake of this demonstrator, set this back to a circular shape, and I can assign to this shape also any parameter. For example, in this case, I'm modifying the radius of the nanostructure in order to create a typical 0 to 360 degree phase control that we are looking to find in any meta surface design, because that control of phase and presumably and ideally at a 100% transmission efficiency gives us the opportunity to create any wavefront, any lens or other type of optical component that we like to see. Importantly, we can also control here the periodic boundary conditions in the RCWA calculation. In this case, I've set this to 400 by 400 nanometer because I'm trying to create a meta surface for the wavelength of 632 nanometer, and then I will move on to set my targets here. It's important to note that any of these parameters that we see here can be parameterized. So for instance, now we've just set the radius, but I could just as easily set the height or the unit cell size as an optimization or sweep parameter. And then I move on to set the metacell targets. In this case, I'm using a very simple design, using just one set of incident light conditions, a plane wave incident under normal incidence, but I could add additional components here with different angles of incidence or different polarization, selecting here any of the predefined conditions, or a Jones or Stokes representation of different polarizations. And I can set this to a sweep validation, but I can also use powerful optimization algorithms that are defined here to optimize my nanostructure for the response that I want. So in this case, I'm sticking to 632 nanometer wavelength at normal incidence, and I don't need to really care about the optimization targets that I'm defining here, and I can go on to move simulation to simulation settings. As I described before, we're optimizing this for different radii to produce different phase and transmission responses. So I have here a sweep variables, different radii. Another important parameter is the accuracy setting of the RCWA calculation. This determines where the Fourier series is truncated in my RCWA calculation. And in practice, this is always a compromise between high accuracy calculations. The higher I set this, the more accurate my calculation will become, but the more time and memory it will consume. So I'm looking for the compromise that gives me converged results so that I can rely on their accuracy without taking excessive amounts of time. For this calculation, I've predefined this as a 6x6 accuracy setting. It's always a good idea to perform a convergence check, and that's very easy to do just by here assigning a parameter. Let's see, well, this is equal to a parameter called orders that I'm changing linearly from 1 to, for example, 20 diffraction orders, and storing that then here. And you see right there my new parameter arrives, and I can set this, but for this demo I'll set this to 6 and keep it at that. And then once I'm happy with my parameter settings, I can move on to start the simulation. So I move on to the simulations tab and click new simulations. For the sake of efficiency, I'll keep the plots that I've predefined, but I can start this here, and this is how you calculate the response of different nanostructures. So what the software is doing now is it is sweeping over any parameter, any setting that we've had, and transferring this to the server for calculations. We use a performant internal server that allows us to quickly iterate through many calculations while not burdening my own machine. So in fact, I could turn off this laptop and still the calculation would keep running and continue, and I can come back after the weekend is over or for an overnight simulation in order to then inspect my results. While this is running, I want to point out that this is a sweep calculation. We could also use, for instance, a parameter optimization using a Bayesian optimizer or a genetic algorithm or any other algorithm of my choosing. While I was talking, the results have finished, and we see here the results of this calculation showing the response of the nanostructure in terms of amplitude at the transmission coefficient here on the y-axis and the phase response on the x-axis. So we see that this particular set of nanostructures has a high transmission while being able for the different radii, the different colors here, to maintain phase control from -pi to 2pi. Now it could be interesting to also look at the plots in a couple of other representations. I can always do that here by adding an additional plot and looking, for instance, at a physical output. In this case, let's say the transmission. Could also look at reflection in the 0,0 diffraction order, the TE polarization versus my sweep variables, in this case the radius. And I'll click update, and this again triggers the server to make a calculation of the nanostructure's response for the different wave radius sizes that I've set. In this case, I've set the radius, but as I mentioned, you can set any other physical parameter that you like and perform similar sweep calculations. So this could be the angle of incidence, the height, or any other optical calculation. And here we see then the transmission response, which is quite typical for these nanostructures. So on the whole, we have a reasonably high transmission, but you see some resonances appear here as well that we generally like to avoid within our calculation. But let's say I'm now happy with this calculation, and I can move on to create a nanostructure or metasurface using this library of metaatoms. The first step I will do here is then to create a library of meta cells, which we call meta cell groups. And this could be either a library that I've defined out of these structures. So in this case, I've made a library of niobium pentoxide structures designed specifically for 632 nanometer. Or I can select PDK structures. PDKs are structures that have been predefined by a manufacturer. That means that they have already been optimized for manufacturing and can be readily sent to the manufacturer already compliant with their design rules so that they can be prototyped rapidly. But let's move on and create our meta component here. So start with a component here below, and when I create a new lens here, so let's say I'm calling this a 632 nanometer lens, sorry, 632 nanometer wavelength lens, of course. I can again go on and set this as I like. So for example, I create a first lens which I would like to be a 500 micron by 500 micron size, and specifically I want to then set the structure group, the library that I've set. So I could use a PDK. In that case, I can send it directly to the manufacturer, or I can use my own defined libraries here, move these over and store them. So what I'm doing now is I'm telling the software algorithm to only use the structures that have been optimized for my design rules that I've selected before to be used inside the meta surface design. And then I can move on to target, which defines the target functionality, the optical functionality that I want my meta surface to achieve. And this can be one or multiple targets. For example, if I'm doing a polarization multiplexed design, and I can add here a new wavelength, a new target. When I'm defining my target, I see that I've defined it for a specific wavelength, for a specific incident angle and incident condition, for a specific incident and outgoing polarization. So we can use this also to create polarization converting meta surfaces, for instance, using the geometric phasor Pancharatan-Berry approach. And then we can define both a far field wavefront using the IFTA approximation algorithm, which will transfer any far field projection to a corresponding phase in the near field, or I can define my optical response, the target response that I want my meta surface to achieve here in this near field wavefront editor. Let's go into the little wizard here for that. So I can select what type of component do I want to achieve. In this case, I'm looking to make a hyperbolic or aspheric lens profile, but I could select any number of predefined component types such as dot pattern arrays, imports from ZMax or other ray tracing programs, gratings, top hat beam profiles. We have complete freedom over the wavefront that we are creating. That is the great advantage of meta surface design. So let's say for now I want to create an aspheric lens. It's been pre-parameterized for a wavelength of 632 nanometer and focal length of, well, I'll put 1000 microns in this case. And let's create a preview of this wavefront here by clicking the preview button, and this will show us the amplitude and phase profile that we're looking to create in this lens. So we have a uniform amplitude because we want unit transmission, and a phase which is giving this characteristic concentric ring profile. Now this is a standard predefined example, but in a lot of cases the strength of meta surfaces is precisely in being able to have complete control over the wavefront that we are creating, and the software allows this by having this script interface which lets you define any phase or amplitude profile that we want. So in this lens case, it's quite straightforward to define phase profile, but I could easily add here additional parameters and program them in any way that I like, or import them directly from an external source. But let's say I'm happy with this hyperbolic lens. and I can generate the target and store this in my metacomponent. And this lets me move on to the next part of the design phase. I've now defined the geometric size of my meta surface. I've designed the ideal performance that I want. So now it's time to move on to design of the meta surface itself. When I click here on the Start Design button, this will place the nanostructures from my library in order to best approximate the target behavior that I've assigned using least square algorithms. So this, in this case, is just one wavefront, but this can also be multiple wavefronts, for instance, in a polarization or wavelength multiplex design, or even doing dispersion engineering, or uploading your own design here through the Upload Design. When I click Start Design, again, this triggers the calculation on our server. So all of this happens without burdening your own PC. It's worth pointing out that our software is also available as an on-premise calculation using dongles such as these. In that case, it runs entirely air-gapped, so there is no internet connection needed at all, and all calculations happen within your own network or on your own computer. While this design is running, you can also see its progress, and it's worth pointing out that any calculation we do here, whenever a wavelength is requested that was not yet in our library, under the hood RCWA calculations are triggered on the fly. And actually our design is finished by now, so I can just look here, our design is done, and we can generate the corresponding GDS file. So let me set that here to 16 polygon points, and we can choose the file that we want. So popular files are Oasis files or GDS files, but we have other options as well. We can click Generate Mask in order to generate the mask and send this to our manufacturing site. So this can be our internal clean room facilities, or can be any manufacturing partner that you work with that can then directly open and run these GDS files. Let's give this a moment to complete. This will download automatically my GDS file here on the site. My GDS is done, and let's open File and inspect our GDS. Voila, and here we have a GDS file which contains several thousands, or in this case, well, we can check, I guess. This is 1250 by 1250, so more than 1 million meta-atoms included in this file. Indeed, if we zoom in, we see our pillar structure, our different sizes that we've defined in a shape that closely resembles our face target, which is not surprising, of course, because the pillar mapping here is a representation of the face. You can see here in the center, we have different pillars going from the center through our meta surface. But this file looks fine, and we can go on to further analyze the performance of the meta surface. We can do this here in these three tabs. On the one hand, there's ODA, overlapping domain analysis of the near or far field of our meta surface, and we can also link this to a ray tracer if we like through DLL interfaces. But let's start with the basics and take a little look at the near field of our meta surface. So once we've designed our meta surface, we do this for a certain design wavelength, but of course in reality our wavelengths could be very different, so we can again here set the different wavelengths at which to run our analysis. So this could be different angles, different polarizations, different wavelengths, or different beam profiles, and then we run using different we run to calculate the near field wavefront of our meta surface. So I will now set this, for instance, at a position of 100 microns with a width of 10 by 10 microns, and I will select my calculation method as well for the wavefront of a metasurface, it's important to realize that a metasurface is huge in terms of its complexity compared to a full wave calculation. So we use various approximations here ranging from fastest and least accurate to slowest but most accurate local periodic approximation, local field approximation, overlapping domain analysis. In this case, I will select the local field approximation and again calculate what my wavefront's near field view will be under this analysis, and then say this is a near field. And run this here. This will once more trigger my server to do the calculation for me. What you're seeing here is the user interface to PlanOpSim software. As you can see, this runs in any browser, but let's assume that I'm very experienced and I'm tired of clicking around. Then there's a useful option. If I go here to downloads, PlanOpSim software contains an SDK software development kit that lets you automate any action I'm taking here in the user interface through Python script, so that whatever I'm doing here can be directly replicated and automated using Python scripts, or in fact any other programming language that can make an HTTP call can make these calls to the PlanOpSim software and let the analysis take its course here. We can use this feature to automate and run thousands of analyses over a long time, or use this to integrate with external programs like a ray tracer or an optimizer of your choosing, in case you don't like the optimizers that are in PlanOpSim software. Voila, and this calculation has now run, and we see the near field wavefront profile, the wavefront right after the metasurface associated with this metasurface. And if we zoom in a little bit here, we can actually see the signature in the near field of each of these nanostructures that we have. So nominally, each of these pillars produces a certain phase, but if we then look in detail, we see that they also have their own amplitude and phase profile locally within the unit cell, and we can analyze this in detail through the near field analysis, or we can look at the optical performance in the far field instead by selecting the here wavefront option far field and setting that to our let's visualize the focal spot. So we got focal length we set at 1 millimeter distance, and we will also want to see what is our MTF of this lens that we've designed. So let's set the spot size in an observation window 15 by 15 micron with 100 step resolution. Here we go. And then trigger this calculation again. We can choose various approximations here again, so the well-known Fraunhofer formulas or the rigorous angular spectrum method, and run a new analysis that I will call the focal spot. And run this here. Again, clicking new analysis triggers this calculation on our server. While we wait for this analysis to run, I want to spend a little bit of time talking also about maximum sizes that can be simulated. As I'm sure you're well aware of, full wave calculations are limited and very time consuming. So they're limited to only a few tens of wavelengths, maybe hundreds of wavelengths in size, before they become extremely time-consuming, or just run your machines out of memory, even if you're using very powerful machines. So in order to simulate practical metasurface sizes, we have to rely on approximations, because even 1 millimeter size, which is a tiny component for a human, it's an enormous component for a full wave calculation. So to do this, we run our metasurface designs using various approximations. The approximations we use here, in combination with the powerful servers on our side, allow us to simulate record-breaking sizes up to around 1 billion scatterers within single metasurfaces. This is 1 billion individual microstructures over a total area. If we use a unit cell size of 500 nanometer, that would be around a 15 millimeter metasurface component. If I take my smartphone, which is the current main application for metasurface devices, where, for instance, in time-of-flight sensors or other 3D sensing applications using structured light, this is well within the maximum size you want in that range. Still, the push in metasurface designs is really to go for ever larger metasurface sizes. In the meantime, my calculation's finished, and I see the focal spot of my meta lens, which of course produces a nice focal spot at the position that I've designed. And I can look at its cross-section here. We see indeed the typical airy disc pattern that is normal for a diffraction limited lens, which was created by the target that we've specified. We can also look at typical lens analysis parameters like the MTF analysis, and indeed we see here that this metasurface creates a lens that is close to the diffraction limit, and we can analyze this further if we like using various different approximations, or if I want to further process this data, for instance, to extract any metric of my choosing, I can just export the raw data and have the full data here for further processing. This is just one lens. If I then want to use this in a ray tracing calculation, I can do so by generating a decomposition here into Zernike coefficients and exporting that via DLL link to different ray tracers. In view of time, I will not do this today, but I just want to point out that it's possible. With this, I'd like to conclude this very short introduction to meta lenses and metasurface design in PlanOpSim. I welcome the floor to any questions that you have, and I want to summarize that using today's powerful metasurface design algorithms, it is really possible and practical to design metasurfaces for any application in a short and practical time in a way that's optimized for industrial applications and integration into complex or simple systems. And I welcome any questions that you have. Thank you very much.